Hello, everyone. Welcome to our final guest lecture for this year. Today we have Nick Scoville, who will be telling us about discrete Morse theory as an introduction to topology. And how do you like people to ask questions?
So people can certainly feel free to interrupt when I'm talking. I know it's a little bit awkward too, but that's okay. They can certainly interrupt or wait till the end as well.
And would you like them to talk aloud or type in the chat?
Oh yeah, probably talk aloud. Yeah, if you could talk aloud, that'd be great.
Okay, sounds good. So go ahead.
All right, great. So thanks a lot for inviting me, Simon. Thank you everyone for being here. I'm so impressed by the work that is going on with you guys. Simon shared with me some of the projects that have been done in the past, and it's really impressive. I'm just blown away at the kind of things you guys are able to accomplish. So I hope I can tell you something interesting and useful for you today. So I do want to talk about, I want to tell you about discrete Morse theory as an introduction to topology. And I'll tell you about a couple of results that I've done with some collaborators, Yu-Ching Liu, Ben Johnson, and Julian Bruggeman. Yu-Ching Liu and Ben Johnson are actually Ursinus undergraduates, or I did this work with them when they were undergraduates. And I've actually done work in discrete Morse theory with high school students as well. So I'm hoping if you find this work interesting that you can easily get into this and do some of this, answer some questions yourselves in this area. So I also have the interesting task today of trying to say something that I hope will appeal to people who have both seen topology and who have not seen topology before. I know you guys are quite advanced and have seen a lot of mathematics, but I'm not going to assume you have seen topology before or know what it is or the kinds of questions we ask. So I'm going to begin by introducing topology, giving kind of a motivation for what it is we do, and then I'll move into discrete Morse theory and some of the research that I've done. So hopefully those of you who have seen topology won't be too bored with the beginning of this talk. So to begin, well, let me give a little bit more detail for an outline. I ultimately want to end up telling you about a couple of little areas of topology called merge trees and persistent homology. You may have heard of these before. And so these are not only interesting areas that a lot of people are working on, there's also some work in discrete Morse theory, which I'll tell you about. Before I tell you about merge trees and persistent homology, though, I'll need to tell you a little bit about discrete topology, what it means to do topology in a discrete setting. And again, I'm not assuming any background in topology. So if you hear the term discrete topology for the first time, this might make you think that there's something called smooth topology or continuous topology, two different kinds of topologies. And of course, these are all under the general heading of topology. So I started from the bottom and worked my way up, but for now I want to start at the top and work my way down by beginning to answer the question of what is topology? What do we mean by topology here? So I think a good working definition of topology is that topology detects and counts holes and their higher dimensional analogs. So if you think about that, okay, that it's not really clear why I might want to do that, why that's interesting, but that seems fairly straightforward at first. There's holes in objects and I'm just kind of counting them. Well, actually, upon a little bit of reflection, this turns out to be kind of a difficult problem from a mathematical perspective, because here I have what I think all of us would agree I'd want to be a hole, but it's not clear how I would define this mathematically. Because if you think about it, a hole is defined by what it isn't, by what is missing or lacking. And so this becomes kind of a weird negative definition. So how do I grasp the concept of what it means to have a hole in something if a hole is defined by what isn't there? So one of the ways that we go about answering this question in topology is we realize that the boundary of a hole, kind of the area around a hole, is essentially a circle. And I've outlined that in red for you. And so the idea of detecting a hole would be essentially to detect a circle or a loop or whatever you might want to call it that surrounds something, but that I can't kind of contract or squeeze to a point. The further you think about this, you realize that I don't really care, though, the fact that it's circular. It could be elongated or elliptical. It could be small. It could be large. It could be anywhere in my workspace. And all of that information, I don't really care about when it comes to the question of detecting holes. So when you start to reflect on this question, you realize a lot of the geometry that we like to think about, distances and angles and precise points, that really doesn't matter so much. All that really seems to matter is that I can kind of find one of these red loops and that I can't kind of contract it down to a single point.
Basically, okay. You can't contract it without moving outside of your space.
Yeah, that's right. The second if I was to try and take that red loop and I was to try to kind of contract it smaller, that's exactly right. I would move into the white outside of the black. That's an excellent way to think about it. Good. Okay. So this is sort of the idea here in topology. Let me get rid of that hole, kind of cover it up. And let me move now to, well, the question of why anyone would care. Why would anyone even want to find holes in things? Maybe it's a fun mathematical exercise, but are there any sort of applications or things people like to do with this? Well, currently in Switzerland now, there is a government-funded project called the Blue Brain Project going on. This is a multi-million-dollar project that has essentially taken an entire rat brain and it has mapped all of the neuron and synapse information onto a computer. So it has the entire rat brain and all the neurons and the connections between them all on a computer, a huge data file, thousands and thousands of neurons and millions of synapses and a lot of information here. They have a lot of different people working on this Blue Brain project. They have biologists and chemists and biochemists, neuroscience and mathematicians, which probably isn't too surprising. But what might be surprising is the fact that the mathematicians they have employed on this project are topologists, not applied mathematicians or people who work in mathematical modeling. Why would they care about topologists? Well, here's one reason why they might want topologists working on this project. I can model neurons, let's say a pair of neurons and the connection between them, a synapse, by this simple diagram here. And if two neurons are connected by a synapse, this information, which is represented by the yellow, is able to travel from one neuron to another. And so we can kind of see that here in this little animation. Okay, that's all well and good. But as I understand it, one thing that neuroscientists are looking for in the brain is evidence of higher structure, higher cognitive structure, which tends to be given in some cases by a kind of loop, where I have a few neurons, maybe hundreds, or maybe just a few in this particular picture, where I can start at one and travel back to that as kind of a feedback loop. And again, as I understand it, I'm not an expert in neuroscience, but this corresponds to kind of higher dimensional or higher cognitive structure in the brain. And people are really interested in finding these kinds of feedback loops in the brain. Well, if you think about it, this structure is kind of modeling a circle or a loop, which I'm going to call S1. This gives me kind of a discrete model of a smooth structure of going around in a circle, so that the question of finding these loops can be thought of as a topological question. Can I find a quote unquote hole in my neuron connections? Well, if a one-dimensional hole corresponds to some structure, maybe a higher dimensional hole corresponds to some higher cognitive functioning in the brain. So I can come up with a mathematical model of a sphere. This is what I'm going to call S2.
Hey, by the way, I have a question about this. So,
sure, Kimberly.
Oh, I don't know what. Oh, well, actually, my name's Dallas. My mom's name is Kimberly. I don't know I think something went weird with my name.
Oh, sorry about that. Okay.
Oh, but it's okay. Okay, so I have a question. So why would we need to do this topological problem if we could just look at where the triangles are and where all those are. Oh, maybe it's because the higher dimensional case is a bit harder. Is that
Good, good, excellent. You answered your own question. So that's great. You're right that if all I'm looking for is the triangles, I don't need topology. I'm using way too complicated mathematics to solve an easy problem. But what you said about these higher dimensional holes, that's precisely what people are looking for here. So
there are tetrahedrons, and there are those, and there are a lot
good,
of,
yeah,
you
like a
name it.
tetrahedron. Good, or it's sort of like a tetrahedron, actually. I guess, depending on how you define it, it's kind of like a pyramid on top of another pyramid. Right, and
But there's all these complicated structures, and like, how can you tell where the holes are? Like, it's a bit hard.
yeah, good, exactly. And what is a higher dimensional hole? This is something someone in the chat mentioned graph theory. That's all this would be if all I cared about was triangles or things where I go around 4 times. But something like this structure, you can think of as modeling a, oops, let's see, am I in this thing here? Yeah, modeling like a sphere, like a basketball, the outside skin of a bowling ball with a hollow interior. These would be the relationships that I might want to see among neurons and synapses. And you could think of this as a graph theory problem, but topology has the tools to detect these holes. Let's see, we can't just do connected components for higher dimensional coordinates, similar to 2 dimensions. I mean, so topology can find connected components, but it can find sort of the higher dimensional analog of connected components. I don't know if that answers the question, which is
also, I have another question.
Sure.
I mean, why, in the case of the neurons, there's also those one-dimensional holes, so like the triangles on the outside. Triangles on the outside aren't covered with anything, so how would it like model a sphere or anything? Like, how do we know there's not something inside the whole diamond, the whole octahedron thingy? Like,
yeah,
what's not inside?
good. So I think the question concerns sort of where I'm drawing these things in space. So if I have this structure in space, the question is, maybe I've got another neuron kind of inside, right? Living inside the tetrahedron, inside the pyramid. Well, for topology, I don't really care about where things are located in space. I only care about the relationships. So we're going to see this.
Well, I'm not really thinking about neurons inside. I'm thinking about the connections inside.
Yeah, so if I'm understanding correctly, there could be other connections inside as well.
But like, okay, like from the top to the bottom, it would be like inside this whole thing, and it's like, so the sphere, maybe the sphere gets filled in, and then it's not.
Yes, okay, that's right. So if I had, and I think the question is, maybe if I had a connection, let's say between the North Pole and the South Pole here, is that your question?
Yeah, or
yeah,
any other connection that would live inside.
Yeah, then that really wouldn't be a topological sphere anymore. It would be something else. It would actually be what's called like a wedge, whatever that means. Oh, no, sorry, it would not. It would be it would be something different. I'll just say that. I don't want to get myself in trouble.
Yeah, but like my point is, like, there's this octahedron, sure, but the triangles aren't covered, so like there's still all these one-dimensional triangle holes.
Yeah, that's right. So so there are the one-dimensional triangles, and let's see what do I want to say to this. Yeah, the topological techniques we have will take into account all the different kinds of relationships that you might see.
Okay.
So yeah, if there's little variations on that, it would detect those. So okay, let me keep going with this. This is my model, or one model of like a 2-dimensional sphere. And even though I can't see it in physical space, I can draw the relationships that would tell me that there's a 3-dimensional sphere. Something like this. Again, this object doesn't live, there's no, we can't draw or we can't visualize a 3 sphere or a sphere that actually lives properly in 4 dimensions, but these are the relationships that would have to occur, or some relationships between neurons and synapses that would tell me about this higher dimensional sphere. And so the idea being that maybe a structure like this would correspond to higher cognitive function. And so you can go online actually and find there's dozens and dozens of papers that have come out of the Blue Brain Project, and there are some on topology, and they've found some interesting things with very high dimensional spheres there. I think the jury's still out on exactly what it corresponds to, but if nothing else, topology can kind of provide a tool, a new way of studying a very complicated structure that we don't otherwise have any clue, what to throw at it. So it can find some structures that we wouldn't normally think of. Okay, I'm not an expert in neurons and the Blue Brain Project and things, but this is just to give you some idea of the kinds of new venues that topology is looking at in this day and age, which I think is really exciting. So moving then from the Blue Brain Project and a little bit of application, let me then move to discrete topology and start to give you a little bit of detail about how we build these objects that I was showing you here. So here is a circle, kind of a perfect smooth circle. And as we saw before, I can just kind of model this circle with points and lines. Actually, though, these aren't really points and lines in space. These don't really have distances between them. These are simply relationships between things, as we'll see in a moment. So let me get rid of the sort of smooth circle and define this object. I'm going to call the dots or vertices A, B, and C, and I'm going to define my object of interest here. It's called the simplicial complex, and what it is a finite collection of sets. The sets are called simplices, with the property that it is closed under subsets. So basically, I have a bunch of sets, and I make sure that I throw in all the subsets of any set that I have in there, and I've got this simplicial complex. And we'll write down an example of this in a second. I also want to give a little bit of terminology. Sigma is a coface of tau, and tau is a face of sigma if sigma is contained in tau. So to give a kind of mathematical look at this, I'm going to give names to the quote-unquote edges between them, AB, AC, BC. And I'll define my simplicial complex here as a set, as I mentioned, as I show down below. So I've got my simplicial complex is A, B, C, AB, AC, BC. Strictly speaking, all the things inside the set are actually sets themselves, right? Little a should be the set containing A, AB really should be the set containing A and B, but we suppress the notation, otherwise things get really, really nasty. And lots
and
of
also it should be
sets.
the empty set.
Yeah, that's a good question. The empty set, I didn't put non-empty in there. I probably should have. There's kind of a debate on whether or not you include the empty set or not, and I probably should have said non-empty. So that is a good point.
So basically, sigma is in K, and tau is a non-empty subset of sigma, then tau is in K, and K has to only contain non-empty sets.
That's right. Yeah, that's right.
Should K contain ABC?
Sorry?
Should K contain like ABC?
Good question. Should K contain ABC? The way I've drawn the picture, and actually you've done a nice job of anticipating what I'm going to do next. The way I've drawn the picture communicates to the reader no, because I have not filled it in. However, if you look at the definition, all I need to do is say I'm closed under subsets. And so I've chosen not to throw ABC in there. And so that's cool. However, as I said, you anticipated what I'm going to do next. I'm going to shade that in to try to communicate to the reader, I want to include ABC now. And so I'm going to add that into my definition up there. I'll add in ABC. And so when I'm defining simplicial complexes, I can choose either to fill things in or not. And you say, well, how do you know what you're trying to communicate? The picture's unclear. We can always go back to the set theory definition, which is the ultimate grounding. And so you can see in the set theory definition, there's no notion of distance or length or position or anything like that. It's simply points and relationships between them.
So are all these single element subsets, and what are they actually representing each one? A, B, C, A, B, C, B, C?
Yeah, so little a, little b, and little c represent just a single element. And then like AB, for example, up here represents the set containing A and B. And ABC represents the set containing ABC. Does that answer your question?
Well, I guess that A is like the set containing A.
That's
It's
right.
called the singleton set if it only contains one thing.
That's
but
right.
The other, besides A, B, and C, contain other things. Where we're just not using the set theory notation because it gets like, ugh.
That's right. Exactly. That's exactly right. So it gets, it's a little annoying at first, but then you get used to it. And it's like, it's much cleaner just to concatenate the elements rather than put them in set notation. So I can do a few things with this. I can kind of, again, just playing around with the definition. If I want to remove, let's say, BC and ABC from my picture, I should remove it from my set up there as well. Okay, and so you can play around with this, define lots of different simplicial complexes, and you can think of as corresponding to these kinds of pictures representing relationships between objects. Okay, that's all well and good.
Mm-hmm.
So
yeah. Oh, and one good thing to mention is like, say if you have that triangle, let's say you do like those 3 points, and just 2 of those sides and the whole like interface. That's not a simplicial complex because because ABC is in there, but a subset of that is AC, which is not in there, so it's not a simplicial complex.
Yeah, I think
like that's one example. Like
yeah,
if there's like everything has to be like closed in. If it's bound, like everything has to be closed in by some boundary. Can't. Yeah.
Exactly. Good. You have to have the boundary. I can't just pull B out of here. That's right. For a simplicial complex. Good. Yep, that's exactly the way to think about it. So what I want to do next, here's another example of a simplicial complex. I want to start going back to this question of detecting holes in these things and how I can simplify these objects, but while still retaining the holes. So here's what I'm going to do. If you look in the top right, I've colored some simplices green. I've colored the edge in a dark green and the face in kind of a lighter green. I'm going to call this pair a free pair. And the definition of a free pair is it's a simplex and one of its faces with the property that sigma has no other coface. So what I mean by that is, if you look at this dark green edge, it's a boundary of this light green triangle, but it's not a boundary of any other triangle. So it's only got the one guy. If you have one of these things, we call it a free pair. And it's not too hard to show that if I have a free pair, I can kind of pull it off and I'll still have a simplicial complex. And I'm not going to actually kill any holes. So this is what I want to do. I want to find these free pairs. There's another one. This edge with this 2 face here, I can pull it off. I don't need to do just 1 and 2 dimensional things. I can take this green vertex and its edge. This vertex is only on the boundary of a single edge, and I can pull it off. Every time I pull off one of these free pairs, I'm going to refer to it as an elementary collapse. So now the name of the game is, you hand me a simplicial complex. I'm interested in the holes in it. I'm just going to start pulling off free pairs, performing elementary collapses everywhere I can. So there's one, there's another one. I'm just going to keep going as long as I can. Grab that, pull that guy out, pull that guy out. And at this point, I'm stuck. If I look, I have no more faces, and every vertex is on the boundary of at least 2 edges. So I'm stuck here. I can't do any more free elementary collapses. Well, I want to keep going. So here's what I'm going to suggest I do next. I'm going to pick some random edge, and I'm going to call it, or I'm going to color it there in red. And what I'm going to do is I'm going to rip it out. But if I rip it out, you notice that I kill that hole. I used to have a hole there, but now it's gone. And so because I have changed the topology, or I've ripped this out, I'm going to keep track of that thing that I ripped out there on the right-hand side. But these collapses, they don't do anything. So I'm keeping track of what I ripped out over there. And oh, hey, now I can keep doing these elementary collapses. So collapse, I'll collapse that down, keep collapsing as far as I can. And once again, I get stuck. Well, that's okay. I've come up with this rule that if I get stuck, I can just grab something, rip it out, but keep track of it there on the right-hand side. So now I've ripped two things out. Fine, that's okay. I keep doing collapses. I'm left with a single vertex. It's by itself. So I'll also record that as well. So when the smoke clears, I've performed these elementary collapses, and I ended up ripping out two edges and ended with a single vertex. So that is kind of the data of what I just did. How that is going to tell me about the topology of the holes, we'll get to that in a little bit. It looks like, oh, I have a hand raised.
Yeah.
Please.
What would you call ripping out an edge? Like, what's the formal definition for it?
Good. I'm so glad you asked. I'm going to get to those. So I'll tell you right now, it's going to be called critical, or a critical edge, or a critical vertex. But I will actually give the formal definition of this in a couple slides. Excellent. In fact, I think I'm going to give, let's see, I want to give this now here and show you how this corresponds to what I just did. So the idea now is that, okay, I just did all these elementary collapses, and I was able to kind of tell you this in real time and show animations of it. But if I wanted to write this down on a piece of paper and communicate it to a reader, how in the world would I do that? Well, this is what I want to do next, and I think this will help answer the question that I was just asked about the names of these things. So to make a formal definition of what we just did, I'm going to define something called a discrete vector field to be a matching or collections of pairs of simplices where each simplex is in at most one pair. And I'm going to call these vectors or arrows. Let me give you a few examples of these things here. Below here, I've got 4 examples of discrete vector fields. And basically the arrow means that I have paired the tail of the arrow with, or the tail, let me show you here with this. This arrow here is coming out from this vertex. So that's communicating to the reader that this vertex is paired with this edge. This vertex here is paired with this edge. This vertex is paired with this vertex. This discrete vector field can be communicated through these arrows, and it's alerting the reader to what things we have paired together. Okay, well, if you think about it, I guess I want to give one more definition, and then we'll hopefully tie this together. The next definition I want to give.
Actually, I kind of have a question.
Sure.
So can you go back to the other slide? So, okay, so a matching, so like if you have all these pairs, is there any sort of structure to the pair? Is there anything that the pairs have to satisfy? Is it just any collection of pairs, like any collection of pairs where each simplex is in at most one pair?
Yeah, so right now that's all it is. Anything whatsoever. On the next slide, I'm going to give one more criteria that I want it to satisfy, but right now it's what you see is what you get. This discrete vector field is just that definition.
Got it.
Okay, good. So yeah, the one thing I do want to add to that, to tie into the example we saw earlier about elementary collapses, is this notion of something called a V-path. And I put the technical definition here. It takes a few minutes to just kind of parse out and see what it's saying. But basically the idea of a V-path is if you have a discrete vector field, you're an ant, like a little ant, standing on one of the simplices, and you're just following the arrows. So you're an ant, you just follow the arrows in the directions that they're telling you to go, whatever path you feel like, start wherever you want, stop wherever you want. That's a V-path, just following the arrows. And the one thing I'm going to be interested in here is when you start at some simplex and you are able to follow a path and end up at that same simplex. In other words, to be what's so-called closed. So here's an example of this. If I'm an ant right here, I just follow the arrow, follow the arrow, follow the arrow, and I end up back where I started. That's called a closed V-path. And these are
so
you want to exclude.
You end up, so you're back where you started.
Right. So that's possible to do in a gradient in a discrete vector field. But what I'll want to do is actually exclude that as a possibility in my next slide. So if you take a discrete vector field and you put the requirement that there's no closed v paths, you get something called a gradient vector field, which I claim is precisely what we were doing a few slides ago when we were doing the elementary collapses. If you look at the way the arrows are given on the simplicial complex, these are precisely the collapses that we performed earlier. And so now this starts to address the question of how I can communicate all those collapses to a reader. You can see the arrows telling the reader which pairs to pull off. And in fact, when you look at which simplices do not have arrows on them, I'll color them in red. Those are precisely the ones that are critical. And I think this goes back to a question that someone asked earlier. The things that we ripped out are the things that are not in a pair, in a matching, in my gradient vector field. And we're going to call those critical because, as we saw when we were pulling them out, they changed the topology, or at least they did in our examples. So those seem really important. So now I've got a simplicial complex. I'm going to put a gradient vector field on there. And the things that are not part of a gradient vector field are what we are going to call critical. Okay. So let's look at a couple of, well, at first, non-examples, things that actually violate these definitions. So on the left, I have what's called the triangulation of what some of you may have seen before called the Mobius band, which is you essentially take a piece of paper and you glue the edges together except with a twist. Some of you may have seen M.C. Escher's drawing of ants actually going around a Mobius band. And you can see that I'm trying to communicate the twist by saying this vertex V1 is glued to this V1. This V0 is glued to this V0. So you can think of it as gluing them with a twist. So I'm going to attempt to put a gradient vector field on this, although I'm going to fail, actually. I don't know, it looks pretty good. It looks like I've got a gradient vector field here. I don't know, can anyone see why this is not a gradient vector field? Anyone want to take a guess?
Every vertex has two edges coming out of it.
Let's see. So that's okay to have every vertex having two edges coming out of it. That's no problem. It really has to do with the arrows, though.
There is a closed loop if you go around the outer edge.
The outer edge. Let's see. Actually, let's see. So this is a little bit... Yeah, good. So if I go out the outer edge, I think what this person realized. Well, actually, if I go out this outer edge, I actually come out down here. I come out at the bottom. But what I think is happening here, whoops, is that this vertex V0 is the same. It's critical. But if you look at what I just, this arrow that I highlighted in the red, this V1 actually has two arrows coming out of it. And so it's actually not a matching where everything is in at most one pair. V1 is actually in two different pairs. And so that's illegal. So that's a little bit subtle because, it looks okay, but V1 is in two pairs actually.
Also, another thing is like, actually, well, one thing I want to mention is actually those arrows it's not like those arrows are going there because that line is connected. The dot is connected to that line with no arrow from that line back to that dot. I just want to point that detail out. The arrows aren't moving from dot to dot; they're moving from dot to line.
Yeah, which is okay. I mean, it's communicating to me that I started this dot.
It's just what I wanted to point out, so it's not confusing.
Good. Yeah. No. Thank you. Yeah. And that's, in fact, we can think about that'll be helpful for the next example, which is the.
And also.
Yep.
Ooh, but also these are just non-examples of like vector fields, not non-examples of gradient vector fields.
Right. Actually, so the one on the left, it's neither a gradient vector field nor a discrete vector field. I suppose you could say just a general vector field, where I allow anything.
Yeah. At first, I thought you were doing non-examples of gradient vector fields, like, oh, it has a closed loop, but oh, you're just doing a non-example right there. That was just not an example of a vector field.
Well, actually, let's see if anyone can figure out, sort of going off what we just heard, what the problem is with the one on the right, this torus, where now I'm gluing the top to the bottom and the sides together to get kind of this donut shape.
Yeah,
Let's see what the problem there is.
there's a loop.
Good. I've got a loop. I think that one's maybe a little bit easier to see. Let's see, where is it here? Whoops, I gotta make sure I'm back here. Yep, so I've got a loop going from U0 to U0 at the top. And in fact, I also have one towards the bottom where I'm going from an edge to a face, and then I go back around. So I've got two loops here, which is really problematic. So I can actually fix this by grabbing one of these culprits and just pulling the arrow off. So I think that's what I'll do next. Grab some of these culprits, pull the arrow off. That forces them to be critical. But now, in fact, I have a bona fide gradient vector field on both of these examples. And so I can see, well, here's my critical pieces. Yep.
Oh, and by the way, I just want to mention, so basically a loop would just be like, so like it's an arrow that connects a dot to a line. Maybe that line is like, but maybe there's another dot that's part of that line. There's an arrow from a dot to another line, and then it keeps going like that. Not like the arrows go in a loop themselves, because U0 is connected to that line. You would have been connected to that line. It's not like U0 is connected to U1 by the arrows.
Right. And if there, anything that I say and I'm doing with a picture, I think, well, sometimes pictures are a little more helpful, but all of this you can make very precise with like the definitions that I had shown before, which is very combinatorial. And I'll give you, and at the end, I'll actually give you a resource to see all this stuff if you're interested to see all the definitions in more detail. Let me keep moving on then. We saw this as an example of a gradient vector field to communicate how I am doing my collapses. And so this is helpful to a certain extent, but one thing that we're missing is the order. If you remember, I started pulling these things off in a certain order, and if all I do is draw arrows for you, I am losing that order. So the one way we can sort of address that is by replacing an arrow with a labeling of the simplices, a labeling of a real valued function. So if you remember, the first thing that I pulled off was that arrow there on the top, or the simplices on the top right corner. I'm going to label those by 20, 20. Why the number 20? It doesn't matter. But what does matter is that they're labeled with the same number, communicating to the reader that they come off together. The next thing that got pulled off was this thing on the left, and I'm going to write those as 19, 19. Again, communicating to the reader that one, those things are pulled off together, the 19s, and it comes after 20. So you first pull off 20, then down to 19, then I move to 18, 18. And you can sort of see that this is a simple way to address the issue of the ordering. 17, 17, 16, 16, 15, 15. I get stuck, and the first critical edge that we pulled off gets its own unique number. So this is one way to alert the reader that, hey, this thing's critical. It's by itself. There's no partner for 11. 11 is by itself, and so this must be critical. And so I keep going. This is giving us kind of an alternative way to communicate to a reader what we did with pulling off these simplices. And so what we've done is we've created something called a discrete Morse function, which is a different way of looking at these gradient vector fields. So here's the definition. Again, it's kind of a technical definition. You can read it and work through it, but it's doing exactly what we kind of said above. Things that I want to pull off together in a pair are labeled with the same number. Something that has its own unique number is going to be critical, which I think I say next, or maybe on the next slide. And this is another way, again, to communicate one of these discrete Morse functions. I guess I'll say here that if you have a discrete Morse function, if a value is all by itself, I'm going to call that critical. And if it's not, I'm going to call that regular. So one thing that you may have noticed, I kind of hinted at it a little bit, is the following. I guess I really want to show you this last line here, that when you put a discrete Morse function on a simplicial complex, it partitions all of your simplices into 3 sets: critical, tail, and head of an arrow. And you can sort of see that at the bottom here. I put this technical exclusion lemma here. This is sort of where this fact down here follows from. But everything that we saw, it's either the tail of an arrow, it's the head of an arrow, or it's critical, and it's never more than one of those. So with this discrete Morse function, these gradient vector fields, however you want to think about them, it partitions my simplicial complex into these 3 pieces. Okay, one, again, very quick example, and this is not a very interesting example of a discrete Morse function on a simplicial complex where I make all the simplices critical. It's a fairly straightforward algorithm where I can just label all the vertices with a number and keep increasing, all the edges next and keep increasing the number, then all the faces with a number and keep increasing. This is going to be a discrete Morse function. It's not a very interesting one. There's not a lot of things happening, but this is one example, and it shows that every simplicial complex has a discrete Morse function on it. Okay, a little bit about discrete Morse theory. Next, though, I do want to get into what I think is going to be a little bit more interesting, which is persistent homology, and then onto merge trees. So some of you may have heard of persistent homology or persistence. And so this is something that a lot of people think about, and I'll give you the general idea of persistence, and then I'll show you how you can apply discrete Morse theory to it. So let's say I have a sampling of points from some sort of unknown object. I have an object, I don't know what it is, I don't know what it looks like, but I grabbed a sampling of points, and this is the sampling that I get in space. You can imagine that maybe the underlying object it's coming from is something like this, kind of a thickened ellipse with a bar in between. Okay, great. So how can I determine or come up with some sort of justification for what kind of object this is lying underneath? Well, one thing I can do is I could maybe draw a disk around each point to kind of approximate the object. And maybe anytime 2 disks intersect with one another, I'll draw a line between them. And then I'll get rid of the disks. And so this will give me an approximation of the underlying object. Well, okay, that's an interesting idea. But as you can see, the approximation that I get, it's very dependent on my choice of radius of the disk. I chose a fairly small radius, and so I got a fairly kind of spread out object. And this is very sensitive, because if I choose a really small radius, I'm not going to get any connections. And if I choose my radius too large, I'm going to get everything connected to everything, and I really lose any kind of interesting information. So the question then becomes, how do I pick the right choice of radius of this disk? And what persistence says is choose all of them. So let's see, I've got a hand raised.
Yeah, so I was just wondering, like, so are we gonna do, like, my idea was you do the radius, you increase the radius, and when you get a connection, you do it. And then if 2 things and if something is connected to something already, then don't connect it when you increase the radius.
I think you're on the right track. Yeah. So what we're going to see, I mean, this idea of increasing the radius throughout time continuously and keeping track of the data I'm seeing, which I think is what you're getting at, is precisely what we want to be doing here. So let me kind of show you, just start out with this, and then I'll show you what kind of data I want to keep track of. So I'm going to start to increase this radius a little bit, which again, I think is what I was hearing. Oops, let's see here. Yep. And, you know, as things touch each other, I'm going to make the connections. But what I want to do is show you exactly the data that I'm going to keep track of. Okay, so I'm going to kind of zoom into one of these pieces and show you what I'm going to do here. So here are 5 vertices, and I'm going to represent the fact that there are 5 separate pieces by 5 dark blue dots in the top left corner. What I'm going to do is I'm going to grow a radius around each dot, each point, and as the radius increases, we're going to see a bar, we're going to see bars emanate from the left-hand, the dots in the top left-hand corner. And they're going to correspond to components. I have 5 separate components. And when components join up together, I'm going to cut off the bars. So let's see this in real time. I don't think I explained that too well. Let's see this in real time. I'm going to begin to grow these disks, 5 separate pieces. Now 2 of them were joined up. Now 2 more. Now those guys were joined. I'm going to pause here. And you notice that I started with 5 separate components, and 3 of them have been cut off. And I'm down to 2 separate pieces that are still alive. And that's in fact represented by the fact that I've got 1 connected piece, 2 connected pieces. And so I'm going to continue to grow these and keep track of the number of separate components. So we're going to see in a second that these 2 components are going to be kind of merged into 1. There we go. And I'm going to pause right here because there's a second piece of information I want to keep track of. Namely, if I have a hole or a cycle, part of the convention is going to be that if I have a triangle, I'm just going to automatically fill that in. That's not very interesting. But if I have like 4 in a row, that tells me there might be a hole there. And so a red dot is going to correspond to the existence of a hole. And what we're going to see here in a second is that this hole is going to get filled in very quickly. So the hole is going to grow, but then be filled in very quickly once these 2 guys end up touching each other. So we're going to get a very short bar corresponding to those. Let's see. Yeah, there we go. So it happened very quickly. So these are the 2 pieces of information I want to keep track of as the radii are growing. I want to keep track of the number of components, and I want to keep track of the number of holes. So what I'm going to do next is show this to you all in real time with the previous picture that we saw. Are we ready for this? Any questions before I do that?
So why aren't we interested in the holes created by triangles? Like there would still be a gap sometimes right in the middle.
Let's see, the holes, when you say a hole created by triangle, do you mean like this little triangle right here?
Yeah.
Or one that has like 4 of them?
Like why did you say that the 4 ones are like what we're looking for, not the triangle?
Yeah, because otherwise, once I have 3 of these that are kind of all connected, what's a good way to say this? There's nothing else coming, so to speak. There's no other evidence. I guess if you were to cover up, if you were to imagine these 2 are gone, the existence of this triangle here corresponds to these 3 disks all touching mutually. And so this is kind of approximating the fact that the 3 disks are mutually touching, and there really is no hole there. In fact, we saw before this was filled in, there really is a little hole here. Here, though, there is not a hole. And when I talk about a hole, I'm talking about the purple. Do you kind of see that? There's a real hole here, but here there isn't.
Okay, makes sense.
All right, so let's do all this now in real time. Let's see how this all goes. So we'll see that as the disks grow, I've got all these components, and as they join up, these bars are being cut off. And now I've detected 2 holes there in the red, and they're still there. They're still alive. They're still alive. They're still alive. Now, ultimately, they're going to be filled in. But what ends up happening here is I now have a kind of summary, a data summary of what we just saw with this bar graph at the bottom. We've got all these little blue lines here, but eventually they get cut out. We've got one long blue line indicating the fact that there is 1 piece. And you see we've got these 3 red lines. This little one here, you can think of this as noise. There was a hole there, but it was born and it died very quickly. That's probably not a real feature of the underlying surface. Whereas these 2 red lines, they lasted a really long time, which gives me evidence that these 2 holes are probably a real feature of this underlying surface. And so this is the idea of persistent homology. It's not only telling you where the holes are, but how long they persist as I'm increasing my threshold. Okay, so there's lots of really cool things people are doing with this persistent homology. Let me briefly tell you some stuff that I'm doing that I did with my undergraduate student Yu-Ching Liu with discrete Morse theory. So what we were looking at was kind of a discrete version of what we just saw earlier. We saw kind of a continuous growing. Let's see what a discrete version would look like. A discrete version would say that start with 0 and draw that, and then draw 1. So if you look on the left, I'm going to be kind of drawing this simplicial complex based on the values, and I'm going to draw it based on the threshold of the numbers. So now this is everything drawn, labeled 1 or less, 2 or less, 3 or less. And what I want to note here is that now I've got 2 components. I've got 2 separate pieces. Here's 4 or less. I still have 2 pieces. Now I guess I'm at 4.5 or less, still 2 separate pieces. By the time I'm at 5, I'm at 3 pieces. Okay, and I keep going. 6 now merges or joins those 2 components. I'm up to now, I think it's 9. You know, the actual numbers don't matter. What really matters is the order, the relationship between everything. So I've got 3 pieces now. Now I'm back down to 2. Now I'm down to 1. I'm back up to 2, still at 2. Now I'm at 3, back down to 2, back down to 1. You can see that as I'm drawing this in stages, there is some data, there's some information about how the components are changing, how many I have, and which ones are joined to which other ones. This is what the question I'm interested in. So what I want to do now is actually do this same creation of this object in real time, where I'm associating to this a barcode, just like I did in the smooth case, but here on the left. These bars are representing births of components and then their deaths. So I just birthed a component, and at the end, this component just gets joined back up. I associate this so-called barcode to this discrete Morse function, which is, again, giving me a data summary of which of components being born and how long they live. So for example, this component was born at time 3 and it died at time 6. This guy was born at time, what is that? 14, maybe 15, and this died at time 20. Birth, death, birth, death. These are actual technical terms, by the way, birth and death. I'm not just making this up. And so the question I was looking at with my undergraduate student was, if you give me a tree and a barcode, can I find a discrete Morse function on that tree that induces that barcode? This is kind of the question that we were looking at. So we were able to prove, I guess we were able to prove the following. We were able to count the number of barcodes that you could induce with a discrete Morse function on a tree. And again, I don't expect you to follow all these details, but the point is, you hand me a tree and I can count the number of barcodes that you could get with a discrete Morse function. And so you get the idea that this is kind of a fun counting combinatorial thing. You know, there's some factorials and 2 to the k. There's probably some fun n choose k things in there that goes on. What I want to show you next is how I actually construct a discrete Morse function given a barcode. And it's kind of a simple algorithm. I'm not going to give you the pseudocode or anything. Rather, I'm going to illustrate it here. So let's say you handed me this graph and this barcode. Can I find a discrete Morse function that induces this barcode? That's the question we were looking at. So the first thing we're going to do is we're going to change all these barcodes into ordered pairs of life and death numbers. So this bottom bar, the component was born at time 0 and it never dies, right? I always have a single component. This next component was born at time 3 and dies at time 6. This next guy, born at time 5, die at time 10, born at 9, die at 11, born at 14, die at 16, born at 15, die at 20. What I want to do is I want to grab some edges and rip them off to give myself a one-to-one correspondence between these ordered pairs of birth and death numbers and components. So I have what? 1, 2, 3, 4, 5, 6 ordered pairs of birth and death. And I've got 1, 2, 3, 4, 5, 6 components. That's what I want to do. And for each ordered pair, I'm going to associate a birth time to a vertex. So I'll grab one component and I'll pick that vertex to be 0. I'm going to grab another component. I'll pick that to be 3. Next comes 5. And I'll grab another component and label that 5. It doesn't matter so much as long as each component gets its own birth time. 9 is associated to that. 14 there. And 15 is going to be there. So that these numbers are now representing births of these components. What I'm going to do next is put some regular values on these components so that I've got 1, 1, 2, 2, all these little noisy pieces, these regular collapses, they come in. And now I'm going to put the edges back in. Those are going to be critical. Those are going to be like the death times or these death edges. And then I'm going to take these death numbers on the left. This sounds very morbid. It's not really that morbid, I promise you. I'm going to take these numbers on the left, though, associate them to these edges. And now through this algorithm, I have constructed a discrete Morse function on this graph that's going to give me exactly the barcode that we saw earlier. So once again, to see that same animation, we can see a birth of 3. Now a birth, 3 is going to die. See, it's connected up. We're going to see a birth, a death, another death. Nothing's going on. Nothing's happening. Birth, birth, death, and then there's going to be a death at the end. Okay, so I don't expect you to follow all these details, but you can see, again, this is something that if you spend some time working on, you could pretty easily understand this. There's not a whole lot of complicated mathematics. There's some counting, things like this. I think it's a very interesting problem, and I had a lot of fun working on this with my undergraduate student. So let's see. I only have 3 minutes left, and I have a whole thing with merge trees here. Maybe, let's see. Maybe I won't tell you what I did with merge trees, but maybe let me tell you what a merge tree is, because I think this is pretty cool. I think you'll like this. So I won't tell you about discrete Morse theory for merge trees, but let me just tell you about merge trees. I don't know if any of you have ever seen the Incredibles, where there's that scene in the Incredibles where Mr. Incredible is hiding from Syndrome in a cave, and Syndrome sends in this little thing to try and find him, and it's got this laser, and it's scanning the area with this laser, and Mr. Incredible hides behind a big rock, and that's so the laser doesn't see Mr. Incredible because he's hiding behind the rock. And so what I want to do is say, okay, what kind of data, what kind of information might that thing that Syndrome sent in have been taking in? So you can imagine that this blue contour is the outline of some rocks in a cave. And so I'll kind of shade that in with the gray. And you can imagine Syndrome's laser from the other side. This is what it's doing. It's scanning the area. And of course, it's stopped. It can't scan past the rocks. It's stopped by the rocks. So as it's scanning the area, what kind of data could it be taking in? What kind of information could it be looking at? So here's what I want to do. I want to go slowly through its laser and notice that at the bottom right-hand corner, what Syndrome's laser detects is kind of an opening right there. It's detected an opening, but nothing else. So it's going to keep going up. And oh, look at this. It's detected another opening. So far, I know I've got one opening and another opening, but that's all I know. I'm taking in very sparse information. I don't have a lot of geometric information that I'm taking in. Maybe it's a very cheap sensor. I just know that I've got kind of these 2 openings. I found another opening. Now I've got 3 openings that I've found. That's all I know. I don't know where they are in space. I don't know if they're connected. This is the only information I know. I found a 4th opening. You see that there on the left. Little 5th opening there. A tiny one. But now what my laser is going to notice is that, that 4th and 5th opening, they've come together in a single opening. They have merged. So what Syndrome's laser noticed is that it had 5 openings, and it knows which 2 of the openings kind of joined up together and merged with each other. So it knows there's kind of a way to get from this crevice to this crevice. There's another opening it found. Oh, and now it sees that there's a way to go from this crevice to the 2 that it's found earlier. And I'll keep going. Now it sees that there's an opening between these 2. Now this is merged with that. And ultimately, when it gets to the top, it sees that there's a merging between all of them. And I'm going to do this in real time and draw a diagram for you in a second. But I see I have a question, and then I'm going to end because I don't want to. And now I can construct a barcode exactly. Actually, I'm going to construct something with a little bit more data than a barcode, because what this will tell me, a barcode just tells me when something is born and dies. It doesn't tell me who was merged with who, but a merge tree will actually tell me which components are merged with which other ones. So let me do this in real time now. We'll draw this merge tree, which is like a barcode on the bottom, as we're seeing this laser go up. So I've got the 1 component, the second one, the third one, and I'm seeing when they come up. But now you'll see how they merge together, how my thing at the bottom tells me which openings, which components, which pieces were merged with which other ones. And so this merge tree now is, again, another data summary of what we're seeing, except it's telling me a little bit more information. If I can just take 2 minutes, let me show you one other example, and then I'll be done, because I think you'll like this example as well, especially if you're interested in data and clustering. So I can do the same question about, here's a bunch of data. How do I cluster it? Which data belongs with it, which other data? Are these the clusters that I want to do? You've heard of clustering. You know you want to group like data with like data, but it's not at all obvious which data to group with which other data. So we run into the same problem. If you make your clusters too small, everybody's got their own cluster. If you make it too large, everybody's together. A merge tree will cluster all of your data simultaneously. So this is really cool. Let me show you this. I'm going to once again grow these disks, and I'm going to have a merge tree at the bottom. And so when pieces are connected with each other up top, the merge tree is going to say when they're connected on the bottom. And this can correspond to how to cluster. And so this is really cool. Let me just quick show you this, then I'll be done. If I take my orange bar there all the way to the left of the merge tree, it tells me to cluster everything in its own cluster. If I move this bar a little bit to the right, maybe over here, this is telling me how to cluster it, how to cluster the data. If I move it a little bit further, just in this one sweet spot, this is telling me how to cluster. I have here 1, 2, 3, 4 clusters. That corresponds to 1, 2, 3, 4 intersections of this orange bar with this black merge tree here. And then, of course, if I go all the way to the end, it's telling me to cluster it all together. So merge trees, very general kind of thing that people are really interested in, tells you a lot. And there's a lot of, I think, neat things with the discrete Morse theory that you can do with it, which I'm going to have to skip over. So I'm just going to quick skip to the end. Sorry. There's colors, there's merge trees, there's pictures. Whoop. And then I guess the last thing I wanted to do is I wanted to tell you that if you do find this stuff interesting, I know you have projects that you're going to be doing, or maybe you just want to do this for fun. I did write a book on discrete Morse theory, published by the AMS in the Student Mathematical Library. Simon was someone who actually read part of it for me and gave me a lot of really nice feedback. I think it's a very readable book. I wrote it for undergraduates, and I've actually worked with, as I said, not only undergraduates, but high school students in projects in discrete Morse theory. So if you're interested in this stuff, this book is a good resource for you. Otherwise, I'm also happy to talk with you. You can find my email pretty easily about anything you might want to. But I guess for now, I'll stop there, and thank you all very much for your attention.
Thanks for a great talk. Bill, are there any questions?
Let's see, I've got one in the chat. Oh, thank you. Yeah, thank you. You're welcome.
Yeah, thanks.
Okay, I guess there aren't any.
Yeah. We talked a lot during the talk, so that was, yeah, that's all good. So
Yeah, so thanks, and I'll see you in a few days.
absolutely, yeah. Thanks, everybody.
Okay, bye.
Bye.
Yeah, thanks. Bye.